So we've already been doing some kind of informal switching back and forth between heights in inches and number of standard deviations above or below the mean. Doing that, going towards standard deviations as a unit of measurement, is what we refer to as the z-score, or converting data into z-scores based on the assumption that it's from a normal distribution. So any variable that is normally distributed, you can convert it to this scale of the z-score just by subtracting the mean and dividing by the standard deviation. So in that case of the mean of 65 and the standard deviation of 3.5, by subtracting 6.5 and dividing by 3.5, we were converting into a number of standard deviations, or we were converting data to a z-score. Now when you convert a normally distributed variable to a z-score, when you plot it, normal distribution is a normal distribution. It looks the same. It's this bell curve. The only thing that changes is your x-axis. So whatever your x-axis was before, whether it was height or heart rate or whatever, after you convert it to the z-score, it will look like this, with centered at 0 and then almost all of your data between -3 and 3. This is actually probably not very accurate because -3 should be out somewhere further out here. This is called the standard normal distribution, because no matter what normal distribution you started with, after you do this transformation, it's the standard normal distribution. And they all look the same. They all are centered at 0 and will have 99.7% of the values between -3 and 3. They'll follow that empirical rule. And the biggest advantage to taking measurements and converting them to z-scores is that you can use the standard normal distribution for calculating probabilities. And the standard normal distribution, there are tables of. There's one in the back of your textbook. They're online. You can pick out the one you like and you can use it. This is what the one in the back of your textbook looks like. It actually gives, it's a nice one because it gives both, it gives probabilities for negative values of z and positive values of z. A lot of tables of the standard normal distribution don't do that. They'll only give you one of them. Anyone want to hazard a guess as to why? Suppose you had a table that only gave you the area, the shaded area for negative z, and then didn't give you anything for the positive z's. What would you do? 1 minus. Yeah. Yeah, you could, if you wanted this probability, so let's say this is 2, you would have to look up the value for -2 and then go 1 minus that, and you'd get the same answer, but it's there's less room for making a mistake if you can just look it up directly. All right, so this is a screenshot from table B.1 of the Open Intro Stat textbook. Now let's use this table to find the probability that a normal random variable takes a value less than 1.43 standard deviations above the mean. So a z-score of 1.43 or less. So putting this in the context of women's heights, what would this mean? What probability would you be calculating here? So this is, the z-score, this is just math, but in terms of something concrete like women's heights, what would this question be asking? Yes? Yeah, it would be what's the proportion of women with a height less than 1.43 standard deviations above the mean, which would be 65 plus 3.5 times 1.43. So whatever that works out to, it would be what's the probability of having a randomly selected woman, or the proportion of women in a very large group of people who have a height of less than that amount. So since we have the positive z-values here, we can just look this up directly. And the way you do it is you go scan down the left to 1.4, and then you go, here's the 0.03. So you find where those meet. You get your first decimal place on the left column, and the second, or you get the first decimal place by going down the rows, and then the second decimal place by moving across. And we get 0.9236, and that's the answer. So if you take 65 inches plus 3.5 times 1.43, that's going to be, I don't know, about 70 inches or so. This is saying that 92.36% of women from that population will have a height less than that amount. And then conversely, the probability that the variable takes a value greater than that will be 1 minus this answer, 1 minus 0.9236, which is 0.07. So far, so good. Here's a few more important z-values. The only one here actually that is really important, and probably you should commit to memory, not because you have to, but because you should just recognize it, is this one, the z-value of 1.96, because it's going to come up over and over. And the reason it comes up is because we often talk about two-tailed significance levels of 0.05. So the probability under the normal distribution of having a value of z either greater than 1.96 or less than minus 1.6, either one of those is 0.025, and when you add them up, it's 0.05. And so that's why this is a very important z-value. You can use the norm.dist function in Excel. Actually, in R, there's something called qnorm, which basically makes any of these questions trivial to do. If you practice doing it a little bit, it's almost like cheating, just so you know. But yeah, it's easy also with norm.dist. You can just put in any z-value or any probability and get the corresponding, either the quantile if it's a probability, or the probability if you put in a z-value. So let's take that one step further quickly here and calculate the probability that a normal random variable falls between minus 1.43 and 1.43 above and below the mean. So before we calculated just the probability of something less than the 1.43, and that was like the 0.92, and the amount, the probability of being above 1.43 and got the 0.07. So these are two equivalent ways that you could think about that. The first one being calculate this probability, the 0.92, and then subtract this probability to the left. You get 0.84. Or you can calculate the area under these two tails, add them together, and subtract that from 1 and get the same answer either way. So it just depends on how you want to think about it. So I'm going to make this suggestion that when solving problems, with the normal curve and with other distributions that we do to actually go ahead and draw yourself a sketch of it and shade the area that you want. And this, I don't know, even though you have software that will calculate probabilities for you, this is a good idea to do, particularly when it comes to doing a one-tailed test, which we're going to show, or either because you are only interested in a one-sided alternative hypothesis, which we haven't covered yet, or because something is an inherently one-sided test. It lets you, pardon me, drawing this out lets you know what the probability is that you're calculating and will help you to know that your answer is at least in the right ballpark. So, you can, by doing this, know that, if you get a value of a p-value of 0.99 when you're expecting a 0.01, you might figure out that there's something up. It's just a good way to be sure that you understand what you're doing. One way that you can use the Z table is like we did. You want to look something up for a particular value of Z, but you may also want to do it in reverse, which is you have a certain probability and you want to get the corresponding Z value. You can do that with the table just by looking up the probability and reading backwards the row and the column to get the Z value. And in software, it'll be called a quantile function. Like in R, it's the Q norm function. In Excel, it's, what is it? I think it's still norm.dist, but then there's an argument in it for getting a quantile. And that's, again, if you get that wrong, if you're calculating the quantile when you meant to calculate the probability, you might still get a value, but it would just be wrong. Of course, you would know if you put in a negative value, like Z of -1, and tried to calculate a quantile, because it would be expecting you to provide a probability when calculating a quantile. So if you put in a negative value or something more than 1, you'd get an error. So just remember that calculating a quantile means you're going from a probability to a z-score, and when you're calculating a probability, it's the other way. You're going from the z-score to the probability. The z-score can be anything. The probability can only be between 0 and 1. So here's an example. What's the value of Z for a cumulative probability of 0.025? We actually can figure this out from the empirical rule, because remember, 95% of the probability was between plus and minus. It was 2, but more accurately, it's actually 1.96. The cumulative probability, or the quantile, the quantile for a probability of 0.025 is minus 1.96 on the Z scale, the standard normal distribution. Remember, quantile, the quantile for 0.025, that's the value for which 2.5% of the probability is less than that. Everyone recall the quantile from, I think that was our first class or our second class? The quantile being like the percentile when you're talking about, standardized exams. It's like, yeah, it's the probability or the total fraction of values that lie below that particular value. So for the standard normal distribution, minus 1.96 is the 0.025 quantile, or the 2.5 percentile. And 0 would be the 50th percentile. That's why when you enter a probability and want a z-score, it's called a quantile function. All right. So here's just, in case this helps, kind of a step-by-step set of instructions for calculating a probability for normally distributed random variables, which is you state the problem in terms of capital X, the random variable, and lower x, the realization. So, probability of capital X less than 67 centimeters or something like that. Then you standardize X to restate this in terms of the z-score. So then it would be probability of z less than 1 or something if it was below 1 standard deviation. You draw your picture, shade it in, and then find that area using your probability function or table or the empirical